All right, check, check. We're recording. Wanted to go over this section, rewrite the limit as a definite integral. Let's think of these as areas of rectangles where this is the height and this is the base. So this is some function. We're trying to find what function that is. Let's say it's looks like this, some arbitrary curve, even though we know it's a little more specific than that. If this is the first x value right there, we would plug the x value into something in this equation to get the value of the y. And maybe we're cutting pi. It says we're cutting pi into n pieces. What if we're cutting it into 7 pieces? What if this was 7 pi over 7? So 1, 2, 3, 4, 5, 6, 7. This would be 1 pi over 7. This would be 2 pi over 7. This would be 3 pi over 7. So we're trying to find out, what are we plugging k pi over 7 into? But we did 7 specifically, so what are we plugging k pi over n into? Well, that's exactly k pi over n. So we are doing the integral from 0 to pi of sine of x dx. Let's try this one over here. Now, the fact that it's 2 really doesn't change the problem much at all. We're just going from 0 to 2. So we're plugging 2k over n into something. Well, that's exactly 2k over n. So we're integrating from 0 to 2 this time of square root of 1 plus x squared. And then the 2 over n, that's the length of the x. That's how x is changing. This one's a little different because we don't have exactly what we need. We're plugging in k over n, or k times 1 over n, into something right here, or k over n, but we're getting 3k over n. Well, that means we're integrating from 0 to 1 because we're still cutting 1 into n pieces. Square root of 1 plus, well, when I plug, the k over n is going to get replaced by the x because that's each of the x values that we're plugging in. So that's 3x squared dx, and you might see it as 0 to 1 of square root of 1 plus 9x squared dx. I want to get this to say times 1 over n, or times 2 over n, or times 3 over n. And if I do that, if I say this is times 1 over n, then this becomes n to the third. So I'm kind of borrowing one of the n's here. If I write it with sigma notation, that's limit as n approaches infinity of the sum of k equals 1 to n of, well, this is 1 to the third, 2 to the third, 3 to the third, 4 to the third, 5 to the third, and so on. That's what k is doing. It's going 1, 2, 3, 4, 5. This is k to the third over n to the third, and then remember that was n to the fourth, so I have to write this as times 1 over n. Well, this is the base, and this is the function for the height, which ends up being this piece I can rewrite. I'm not going to rewrite the whole thing. I can write it as k over n to the third. So we're integrating from 0 to 1 because we're cutting 1 up into n pieces. And, well, that's just going to be x to the third dx. Let's look at this one. We're cutting 2 into n pieces, so what we're plugging in each time, this would be 2. This would be 1 times 2 over n. This would be 2 times 2 over n. This would be 3 times 2 over n. So we're cutting, we're plugging in 2k over n each time we find the area of a rectangle. But the result ended up being just k over n. Well, that means we're going to integrate from 0 to 2, 0 to 2, of square root of 1 plus, I have to plug this in, and the result is k over n. So there must be a 1/2 in there with it. So this is 1/2, well, not 1/2 x like this. It's going to be a x over 2 squared. That's all inside there. And then dx. So you could also write this 0 to 2, square root of 1 plus x squared over 4 dx. This one already has the 1 over n on the outside. Let's write this as sigma notation. So we kind of get them all to look the same. K equals 1 to infinity of something times 1 over n. And I see that we have 1 pi over 2n, 2 pi over 2n, 3 pi over 2n. So each of these has a 2, but really what we're plugging in is k pi over n, just like we did on the very first one. We're plugging in k pi over n, but each of them has a 2 in there also. So let's go cosine of k pi over 2n is what I see. But the x is going to be k pi over n. So this is the integral from 0 to 1 of cosine of 1/2 x dx, or x over 2. I need to manipulate this to have it say times 1 over n. If we have, this is square root of k over n to the 3/2. And I'm going to borrow 1 from this. I'm going to borrow two halves from 3/2. So I could write this as square root of k over square root of n times 1 over n. So there's the borrowing the 2 halves and leaving the 1/2. We can write this as the limit as n approaches infinity, k equals 1 to n, of square root of k over n, because they're both under a radical, so you can write the whole thing as just one radical, times 1 over n. Well, now we're cutting 1 into n pieces, so 0 to 1, and each of those, if we cut 1 into n pieces, 1, 2, 3, 4, 5, something like this, you'd have 1 times 1 over n, 2 times 1 over n, 3 times 1 over n. But that's just k over n. So you're plugging k over n in for x each time. So this is square root of x dx. This one's certainly the most tricky in my opinion. I need this to say 1 over n. If we multiply the top by square root of n and the bottom by square root of n, we can make this 1 over square root of k, right there, square root of n, we get that one, square root of n, and then square root of n is on top. So this ends up being square root of n over square root of k times 1 over n, and I got the 1 over n. So now I know that we're going from 0 to 1, cutting this up into n pieces, and this is the first, this is 1 times 1 over n, 2 times 1 over n, so that's where you get each of those is k over n. We kind of have an issue here though, because we have the square root of n over k times 1 over n. Well, that's inside there is the reciprocal. So we're the reciprocal of k over n. So we're integrating from 0 to 1 of square root of 1 over x, because it's really the reciprocal, and then dx.